In this module, we're dealing with intermolecular forces. That is, forces between molecules. That's as opposed to intramolecular forces, which would be bonds. Intramolecular forces are within the molecules. These are from one molecule to the other. And intermolecular forces are responsible for many properties of these molecules. So the first type of intermolecular force that we will talk about is called dispersion forces. Sometimes you'll see them called van der Waals forces or induced dipole. For our purposes, these are all the same. Every molecule has these. As long as there's electrons, there are dispersion forces. Now, as far as comparing the strength of the dispersion forces between molecules, the heavier the molecule is, the stronger the dispersion forces are. And also the more surface area, the stronger the dispersion forces are. Well, to explain why this is, let's look at what causes the dispersion forces to exist. Well, all molecules have electrons, and these electrons they're not static. They're not just sitting there. They're always in motion. They're sloshing around. A pretty good picture to have when you're thinking about this is of a water balloon. As you move it around, the water sloshes around. Well, the water is like the electrons. They slosh around all the time. So that at any given instant, you're going to have more water in one end of the balloon than the other, or more electrons in one part of the molecule than the other. Now, because electrons carry negative charge, that means you're going to have more negative charge in one part, and that leaves a positive charge on the other. Now, as these molecules, if it's a gas, a liquid, or solid, as they come close to each other, if the electrons in one of these molecules are sloshing around so that, say there's a positive end here, when they bump into another molecule, that positive charge is going to pull the electrons in the second molecule towards it, creating a negative charge in the second molecule. Now you have opposite charges right next to each other, and they attract each other. Now this is a fairly weak intermolecular force as far as intermolecular forces go, because these electrons are always moving around, and next instant it won't be this way. It might shift the other direction. Now, why does a heavier molecule have stronger dispersion forces than a lighter one? Well, simply because heavier means more protons, which means more electrons. The more electrons there are, the sloshier or the more polarizable that molecule is. It's like a big water balloon compared to a really tiny water balloon. The big one's sloshier. You can move that water around more. You can have a greater shift, so you have a greater magnitude of the electric charges in that heavier molecule. Now, surface area, let's look at that. So, first of all, if we were comparing these two molecules here, we can say right off that this would have weaker dispersion forces than this because this is lighter. This has 1 carbon and 4 hydrogens, about 16 grams per mole. This has 5 carbons and 12 hydrogens, about 72 grams per mole. More electrons, sloshier, stronger dispersion forces. But now let's compare these two guys. This is where the surface area comes in. These are both C5H12. This molecule here, if you were to figure out the geometry about this central carbon, it's tetrahedral. And then about each of these carbons, it's also tetrahedral. So this is roughly a sphere if you were to build this model. This molecule here still has 5 carbons and 12 hydrogens, but it's linear, more or less. Well, it kind of zigzags up and down, but it's if you look at this, take a step back and look at the shape of this, it's like a cylinder. Well, a sphere has less surface area of interaction. Two spheres interacting with each other, touch each other on a smaller surface area than two cylinders, right? Just take two, apples and, put them together and see where they touch. Not very much. So this has more surface area. The more surface area, the more opportunity there are for dispersion forces to arise. The more places there are that these electrons can shift around and attract other molecules. So comparing these two molecules, we would say that this one down here with more surface area has stronger dispersion forces than this one with less surface area. The more spherical a molecule is, the less surface area it has, and the weaker its dispersion forces. All right, now let's look at dipole-dipole forces. Dipole-dipole forces, as opposed to dispersion forces which exist in all molecules, dipole-dipole only exist in molecules that are polar. And we know how to tell if a molecule is polar or not. Right? We draw the Lewis structure, we figure out the molecular geometry, we see if the poles cancel, all that good stuff. Well, let's keep it simple. This is hydrogen chloride, and chlorine has an electronegativity of 3.0. Hydrogen is 2.1. The difference in electronegativity is about 0.9. That makes this a polar covalent bond, and that means it's a polar molecule because there's only two atoms. And so this will exhibit dipole-dipole forces. How do they come about? Well, pretty much the same way as we talked about with dispersion forces, only it's permanent here. So when a molecule of hydrogen chloride bumps into another molecule of hydrogen chloride, if this negative end is pointing this way, when a molecule comes up over here, it's going to orient itself so that its positive end is pointing towards the negative end, because opposites attract and likes repel. It's really Coulomb's law. And so you will get an attractive interaction between the negative end of one and the positive end of the other. And this is a stronger intermolecular force than dispersion forces are. And amongst molecules that have dipole-dipole intermolecular forces, the more polar that molecule is, the stronger those dipole-dipole forces would be. So hydrogen chloride, we would expect to have stronger dipole-dipole forces than hydrogen bromide, because there's a greater difference in electronegativity between chlorine and bromine than there is between bromine and hydrogen. What did I say? Chlorine and hydrogen here. So dipole-dipole. And the last one we're really going to talk about is called hydrogen bonding, which is not really a type of bond, but an intermolecular force. So first of all, the condition for a molecule to have hydrogen bonding is it must have a hydrogen atom that's directly bonded to only one of three types of atoms: nitrogen, oxygen, or fluorine. If it's not the case, it's no hydrogen bonding. And so the way hydrogen bonding occurs is like this. This is hydrogen fluoride. So we have a hydrogen directly attached to a fluorine atom. Now, the hydrogen part of it, okay, the reason that hydrogen is particularly, it forms a particularly strong bond, intermolecular force, is that hydrogen comes to the table with only one electron. And when it's bonded to another atom, that electron is going to most of the time spend its time between the two atoms, leaving the atom, which is basically now just an exposed proton over here, a lot of positive charge. Also, all these three atoms, in almost all of their compounds, will have a lone pair of electrons. That's necessary for hydrogen bonding, because here on this fluorine atom, there are three lone pairs of electrons. Lone pairs of electrons are not involved in a bond, so it's easier for them to be sucked over towards another atom. So this hydrogen, with its exposed positive charge, is sucking a lone pair of electrons towards it, creating a pretty strong attractive force between the positive and the negative here. Hydrogen bonding is the strongest of the three intermolecular forces we've seen. So remember, it has to have a hydrogen atom directly attached to nitrogen, oxygen, or fluorine, and only that case. So the relative strengths of intermolecular forces are dispersion, are weaker than dipole-dipole, which are weaker than hydrogen bonding. Now, you also will see ionic compounds thrown in here. Ionic compounds are not molecular compounds. They're not covalent bonds like we have over here. These attractions between the ions are stronger than any of these three we talked about.